Hello, it's Jason from STEMonline.com. Welcome back. It's been a while, I've been very busy. I'll continue to make more mathematics and physics videos on common topics in calculus, physics, logic, and etc. Okay, so today what we're going to look at is another calculus video. We're going to look at a common thing that comes up in a calculus 2 course in university. Okay, and it's about the power series. Okay, it's about finding the radius of convergence of power series. So I'm going to talk about the theory first, and then we'll get into an actual problem. Okay, step by step. So first off, what is a power series? Okay, so let's talk about power series. So the definition, okay, definition of the power series. Okay, so definition, DEFN, is in the following form, right? F of x, some function f of x, is equal to some infinite series, sum from n equals 0 to infinity, f to the n of a, okay, all over n factorial, okay, times x minus a to the n, okay. This is the power series formula. Okay, so this is called a power series. Power series, or sometimes known as, I don't want to confuse you with terms, but sometimes it's known as a Maclaurin series, right? So sometimes known as a Maclaurin series. Okay. Maclaurin series, Taylor series. Well, in reality, a power series or Maclaurin series, Taylor series, same thing. The only difference is when you have a Taylor series, it's shifted by a units to the right, where here we have a, right? If it was just a power series, regular power series or a Maclaurin series, instead of having a, it would be 0, okay? But it doesn't matter. We're trying to find the radius of convergence for any one of these series, and it's going to be the same type of thing, but it's usually in this format, okay? All right, so that's what a power series looks like, okay? Now, we need to talk about the radius of convergence definition, okay? So radius, so now we look at the radius of convergence. Okay, so the radius of convergence. So the radius of convergence, right, has, the way to find it, it has particular cases when it comes, there's particular cases that show up when we're looking at a power series / Maclaurin series, okay? So there's case one, okay, so one one second here, my pen isn't as good, time to get a new pen from Amazon. So case one is, you're supposed to always take the limit as n approaches infinity of the inverse of the ratio test. So in this case, it will be absolute value of some sequence a subscript n plus 1 all over a subscript n. Okay, a subscript n. And if you find that the limit as n approaches infinity of this ratio is equal to 0, okay, well, first off, this means that when we're doing this is always for every x belonging to some real number in a domain. Your r, right, your radius of convergence, r, I'll call it rc. This r is not the same as this r, this is the reals. This rc is radius of convergence. Radius of convergence will be equivalent to infinity. Okay, so you have to make sure you understand you have to remember each of these cases, okay? All right, so next we have case 2. So case 2. Case 2, okay. Again, you have to take the limit as n goes to infinity, okay, of a subscript n plus 1 all over a subscript n, okay. If you're taking your limits of these sequences and you find it to be equivalent to infinity, well, first off, this means that your x has to equal to c. Sorry, x equals a. So whatever your a value is, whether it's 0 or whatever, 1, 2, 3, 4, whatever, right? I should be saying that, yeah. So whatever your a value is here, that will be equivalent to your x for this case, okay? And it also implies that it converges, okay? It converges. And it also implies that our radius of convergence has to be equivalent to 0, okay? All right, so we have two cases. Let's look at the final case, case 3. Now, case 3, okay, if we take the limit as n goes to infinity of a subscript n plus 1 all over a subscript n, okay, and we find that our limit is less than 1, then we automatically have to write our expression in this form: 1 over the radius of convergence times the absolute value of x minus a, okay, has to be strictly less than 1, okay? All right, so automatically, if we find our limit to be less than 1, we need to write it in this form, right, depending what our a is and what our radius of convergence would be, okay? This would imply, right, I'm writing this another way, because when you have it written in this form, you want to know what your actual radius of convergence is, if that makes sense. So what I mean is, we need to multiply both sides by RC. So multiply both sides by RC, right? So if I multiply both sides by RC times absolute value of x minus a, absolute value smaller than 1, well, this would finally imply that I get absolute value of x minus a, right, is strictly smaller than RC, okay? All right. And whatever this value is, that's my RC. Whatever my absolute value of x minus a is smaller, that's my RC. Okay, so let me just put some stuff over here for case 3. When, I know it's a lot, just bear with me. Okay, so when we have the absolute value of x minus a, okay, is strictly less than capital R, right, implies that we have some convergence, right, converges, okay. And so that's one case. Now, if we have x minus a is greater than r, then it's going to diverge. So it depends what happens when you multiply by your RC on both sides of this equation, right? If your x minus a is strictly smaller than RC, you know it converges. If your x minus a happens to be strictly greater than r, then it diverges, okay? And if we flip the inequality sign, depending if you're multiplying or dividing by a negative sign, you should know that for inequalities, okay? All right. Now, there's another way. Let me see if we talk about anything else here. Okay, so I want you to sort of integrate all of this into your head, right? Just integrate it, make sure it soaks in. Pun intended, integrate, because this is a calculus video. Okay, so let's start looking at a particular problem, okay? So let's look at, let's start off, I need to make some space here. The whiteboard, we have some space. Okay, so let's start off with a problem here, okay? Let's look at this guy, okay? So the question is, we want to find the radius. So question 1, find, okay, just 1 second, find the radius of convergence. Okay, so radius of convergence. Just 1 second. Convergence. For the power series, or the power series, okay, and our power series will be this guy right here. We have the sum from n equals 0 to infinity of n factorial, right? N factorial times x to the n. Okay, so that is the question we are going to look at. Okay. Now, when looking at this problem, right, we need to figure out, okay, we need to figure out a few things here. I need to figure out what my a subscript n is. Okay, you understand? So, what is my a subscript n? What is my sequence? Okay, so my a subscript n, so let's define what a subscript n is. Let a subscript n, okay, equal to n factorial. Okay, so n factorial. 1 second here. N factorial times x to the n. Okay, that is my a subscript n. Okay. So this is what my a subscript n is. All right, so it's just this whole thing here. Right? In reality, this is what I'm saying is that this infinite series, okay, is over a subscript n. All right. Now we have all this information. Okay, we know a subscript n. We also need to know a subscript n plus 1 because that's the only way to use our inverse of the ratio test. Okay, so and let's define what our a subscript n plus 1 is. That would be n plus 1 factorial, right? Because we're putting n plus 1 for every n, times x to the n plus 1. Okay. Now that we have a subscript n and a subscript n plus 1, substitute, so we can use our formula limit as n goes to infinity of absolute value of a subscript n plus 1 all over a subscript n, right? The ratios of these sequences. This is equal to the limit as n goes to infinity of a subscript n plus 1, which was n plus 1 all factorial, right? All factorial times x to the n plus 1 all over a subscript n, which was n factorial, okay, times x to the n. All right, so we have that. My factorials is an explanation. You need to know what a factorial is. Okay, so all right, so then we have this. Now, the way to simplify this is to do the following, right? Right, so we're going to have this equivalent to the limit as n goes to infinity. Absolute value, keep the absolute value there. N plus 1 factorial is just going to be, well, what is n plus 1 factorial? Well, it's going to be n plus 1 times n, okay, times x. First off, I can split this up. X to the n plus 1 power can be simplified as the product bases, right, of x, right? So it becomes x to the n times x, okay, all over n factorial, which will just be n, right? N times x to the n. I'm going to explain the reason for this, right? So the justification for this is because of the fact that n plus 1 factorial, well, let's just use n factorial. We know that the definition of n factorial is equivalent to n times n minus 1 all the way up to a product of n minus r plus 1, right? Something of this nature. So if we had n plus 1 factorial, right? Okay, well, n plus 1 factorial, this is just going to be n plus 1 times n. We're going, now, how do you determine where to stop? You stop where you can see a cancellation in the bottom, We see with n factorial will just be n. I only went up to n for n factorial because you'll notice that this and this will cancel. Okay, so the next step is to notice that this is equivalent to the limit as n approaches infinity. Okay, so 1 sec, n approaches infinity, okay, of the absolute value of n plus 1, okay, the n's cancel, x to the n's cancel, same basis, times x, so n plus 1 times x here, okay, that's all we're left with this. All right, so now the next thing is to split this up somehow. Okay, what I mean by split up, uh, you should know that when you have a product of two values, a and b, right, it's the absolute value, which is equivalent to the absolute value of a times the absolute value of b. Okay, so that means that I can split up my limit case. So my limit now becomes limit as n approaches infinity of the absolute value of n plus 1 times the absolute value of x. First off, there's no absolute value of n plus 1. We already know it's a positive value because absolute values uh, automatically make your number to be greater than 0, only positive values. And since n is positive, it's non-arbitrary. Here it's arbitrary because we don't know what x is, so I'm keeping the x with the absolute value, if that makes sense. Like this, so I'll just put parentheses, n plus 1 times absolute value of x. Okay, so the next thing is, okay, we need to plug in, because we fully simplified it. So you only want to evaluate the limit once you fully simplified everything. Now, it may be indeterminate, it may not be indeterminate. But the point is, you want to make sure that you simplify everything first to make sure you're not getting anything that's indeterminate. In other words, you have to be able to prove that it actually is indeterminate or not by using algebraic methods. So here you'll notice if I plug in n approaches infinity, right, this now gives me infinity times absolute value of x. I know that looks weird, but infinity times any number is always infinity. Okay? Now since, right, therefore, because the limit as n approaches infinity of absolute value of a subscript n plus 1 all over a subscript n is equal to infinity, right? Then what this implies, right? So then this will imply that our sum, right? That our sum from n equals 0 to infinity, okay, of, I believe it was n, let me see what it was again, n factorial times x to the n, right, has a radius of convergence, right, so has an RC value, right, RC value of 0, right, because we know from case 2, when the limit of the inverse of the ratio test is infinity, then our sum of our power series must have a radius of convergence of 0. And that's how you solve radius of convergence problems when you want to determine the radius of convergence of a power series. Okay. I hope this video was to your liking. I hope it helped a lot. Quite often people find series problems more complicated than integrals. I mean, they're not hard, but they're just maybe a bit trickier. So that's why I wanted to take this up. I hope you enjoyed the video. There'll be more math and physics concepts coming up very soon. Okay. Like and subscribe. Spread the word about STEM Online. How we help grades 11 all the way up to second year university students that need help in math and physics courses. Okay. See you next time. Bye-bye.